Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
You're listening to the Good Question Podcast with Richard Jacobs. Our goal is to make each of our guests exclaim, that's a good question. I don't know the answer. Because when that happens, it means you, the listener, may be inspired to learn more beyond the interview and to ask great questions yourself that lead to new insights. In this podcast, we cover historical and current anthropology, comparative religion, and history. Welcome, and let's get started.
Hello, this is Richard Jacobs with the Finding Genius podcast. My guest today is Gary Melnick. He works at the Center for Astrophysics, which is in partnership with Harvard University and the Smithsonian. He's what's called a Principal Investigator. He does sub-millimeter wave astronomy. So we're going to talk about some of the various projects that he's working on. So welcome, Gary.
Good afternoon.
Yeah. Well, if you would, just tell me a little bit about your background. What were your interests until you got into this position? And then we'll talk about your current work.
Okay. Well, it goes back a ways. I'm in my early 70s, so I was a child of the space program in the 60s, which focused my interest on space in general and astronomy specifically. I did my undergraduate and graduate work at Cornell in physics and then in astronomy, respectively, and came to the Center for Astrophysics in 1980. While I was a graduate student, I developed an interest in problems that required observations at wavelengths that were not accessible from the ground, specifically observations that required instrumentation in the infrared and the far infrared. Our eyes are sensitive to light. I'll put this in units that we use in infrared astronomy. Our eyes are sensitive to light between about 0.4 and 0.7 micron. And that's, for those who know, about 4,000 to 7,000 angstrom. But in those units of microns, the problems that I was interested in as a graduate student required going out to between 50 and 200 microns. Again, our eyes are sensitive to 0.4 to 0.7, so it's quite a bit beyond the range our eyes can see. But there's a problem, and the problem is that the Earth's atmosphere blocks those wavelengths of infrared light, meaning if you want to pursue investigation in the far infrared, you need to get above at least 99% of the atmosphere. And in the 70s, that was made possible by a very unique and ingenious set of aircraft that NASA developed, in which a telescope was mounted in the side of the aircraft that allowed you to look upward. And these aircraft flew at altitude of about 40,000 feet and higher, which is above about 99% of the Earth's water vapor, the main absorber. And that was a very productive time early in my career because it was a wavelength range that really had not been well investigated previously because of these difficulties. And that's when my interest in far infrared astronomy really developed roots, because virtually every time we went up to observe, we discovered something new. It was that much of a virgin territory.
Wow.
Once I got to the CFA, I continued doing airborne astronomy, but turned my interest to spaceborne astronomy and have worked on a series of missions since coming to the Center for Astrophysics, funded by NASA and led either by NASA or the European Space Agency.
Quick question here. What would be the lowest Earth orbit telescope possible? Could it be in the upper part of the atmosphere? I mean, like how low could it be where, again, most water vapor is gone and it can see out into space with very little interference?
Right. Well, it can't be too low or atmospheric drag would cause anything orbiting the Earth to have its orbit decay due to friction with the atmosphere. I would be guessing, but, I'm thinking that you need to be above about 100 kilometers or more to have any chance of a space mission lasting even months before the orbit decayed. As an example, 2 missions I've been directly involved in, including the one that we launched a little over a week ago, are at about 650, and the most recent 675 kilometers above the Earth. Now, there are what are called suborbital missions. These are not orbiting the Earth, but NASA does have a program that funds the lofting of telescope by very large helium balloons. These are flown out of Antarctica and can reach altitudes of about 30 kilometers. They're not moving at orbital velocities. They're moving slowly because they're carried by the wind, but they serve the purpose of offering a near space environment in terms of atmospheric interference without the cost of a launch vehicle or an extended mission. These balloon flights typically last a few weeks.
Well, very good. So what are some of the, I don't know, to you, the really interesting projects you're working on right now?
Well, the one that I'm most involved in the moment is a project called SPHEREx. It's been in the news recently. It launched on the evening of March 11th, so not that long ago. And I am one of 3 science leads on this mission. There are 3 science leads because there are 3 major science themes that drove the design of this mission. And I'm involved in a mission that was recently selected. This one is a balloon-borne mission that we hope will fly around 2029, the end of 2029, beginning of 2030.
Okay, so I mean, the current, the SPHEREx, what's it about? What's it looking for? And the goal of the mission?
The 3 main goals, science goals of the mission are in the realm of cosmology, the evolution of galaxies over time, and how the Earth and planets we know are forming around other stars get their key ingredients for life. Those are the 3 main themes of this mission, and I can elaborate to the extent you'd like on each of them.
Yeah, let's step through them. That sounds good. Go ahead.
Okay. Well, the cosmology, let me take one step back and just say that to carry out the observation with such diverse goals as I just mentioned, SPHEREx will be taking spectra of every position on the celestial sphere, on the sky. We are in an orbit that will sweep out an annulus across the sky, a strip across the whole sky, and it will do that every minute of every day. An orbit is about 97 minutes. So in 97 minutes, we do one sweep, a narrow sweep around the whole sky. And over the course of 6 months, we will have obtained spectra between about 0.75 microns. Recall again, our eyes work to about 0.7 microns. So it picks up roughly where our eyes leave off, out to 5 microns. And I'll explain why that's important in a moment. But we sweep around this celestial sphere in this narrow strip. And as the Earth goes around the sun, we cover the entire sky every 6 months. And when we cross the Milky Way, which we do on every orbit, we will do what we call the ICES investigation, and that's connected to this question of how the Earth and other planets obtain their ocean. When we exit the Milky Way in this travel around the celestial sphere. We do cosmology. And then when we get to the cap in the orbit, which we cover on every orbit every day, so we get very deep integration near the north and south pole of our orbit, we do the galaxy evolution over cosmic time. So let me start with the cosmology. The cosmology project is intended to answer the question, I'll use the phraseology of the Washington Post, what put the bang in the Big Bang? We have a model of the universe that is like a movie that runs backward. We've known for almost 100 years that the universe is expanding. So it stands to reason that if you ask yourself what happened at earlier times, you run that movie backward. And when you do that, you quickly come to the visual picture of something like akin to an explosion run backward. And when you do that, you reach a point in time very close to the Big Bang where the entire universe was very, very small. And by very small, I mean subatomic in size. Everything we see in the observable universe was within that subatomic diameter, hard as that is for all of us to imagine. But the energy that were at play at that very, very early time are unknown to us. They're at an energy range that we cannot probe in any terrestrial laboratory. So we have to use the universe as our teacher. And the goal of SPHEREx for cosmology is to try to constrain the physics that drove the Big Bang. What were the physical laws that allowed the universe that we observe today to come into being at this very early time? And let me put a fine point on early. We're talking about a trillionth of a trillionth of a billionth of a second after time equals zero. So this is a 0 point, then 32 zeros and a 1 second after the start of the universe. We believe that the universe underwent a very rapid expansion in this short period of time, which is called inflation. And during this inflationary period, it imbued the universe with a number of characteristics which we observe today. And so SPHEREx is intended to use a large galaxy survey to attempt to determine a question of, was it one field that drove inflation, or was it multiple energy fields that drove inflation? So at the 30,000 foot level, that's the goal of the cosmology part of the mission. The history of galaxy evolution is another goal of the mission, and we're looking to constrain how galaxies evolve at high redshift. And to do that, we will take data that we're able to take to very high signal to noise at the poles of the orbit, because we sample those regions on every orbit. And we will be looking at the total light emitted by galaxies at high redshift, actually over many redshift, to look for the evolution of star formation during the early universe.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Well, before we go too far, I want to ask you some questions about these way too far afield. The Big Bang, what time frame are we, I mean, I know it's in the past, but how far back do you think we'll be able to see? When are we going to run into like a wall of theoretical limits? Is it due to like the uncertainty principle that we can't see beyond a certain point?
Well, right. We think the models, the theories that guide us at the moment suggest that this period of inflation that really established many of the characteristics of our current observable universe all transpired in that first fraction of a second, this 0.32 zeros in 1 second after the start of time, the start of the Big Bang. That's probably close to as far back as we can get. There are quantum mechanical limits, the uncertainty principle and the Planck time, that suggests that it's unlikely that we can investigate the universe less than 0.40 or 42 zeros in 1 second after time began, after the start of the Big Bang. But all of the action that we're interested in happened between roughly 10 to the minus 42 seconds to 10 to the minus 32 seconds after the Big Bang. And that's as far back as I'm aware that we can investigate. But that would be a huge achievement given the many, many unknowns that still exist about what happened in that first instant.
Okay. And then, all right, I don't know, what did happen in that first instant that we do know?
Well, what we think happened is that the universe underwent a faster than light expansion and then slowed down after 10 to the minus 32 seconds after the Big Bang. And what makes us think that that happened are a couple things. One is you may have heard of these missions that were spectacular successes dating back to roughly 1990 that measured what's called the cosmic microwave background. This is a image of the universe when it was about 380,000 years old. And that image shows something quite remarkable. It shows that the temperature variation across the universe was very minute, on the order of 1 part in 100,000 between any 2 points you look at on the celestial sphere. And if you stop to think about it, that's a remarkable finding, because if you stand on the Earth and you look in one direction and measure the temperature of the cosmic microwave background, and then you look 180 degrees away in another direction and measure the temperature of the cosmic background, they agree to within 1 part in 100,000. And yet the light from those two opposite directions have been traveling for the age of the universe. And so they could not have communicated with each other to say, let's be this same temperature, unless they were in very close proximity at the beginning of the universe. And so that's one of the things that make people think that inflation or something like inflation occurred. Another is,
Wouldn't there be a speed in the other direction that's lowering the perceived light speed, making it less than c?
no, the speed of light is constant in all directions. So that wouldn't explain it. I mean, there are small effects due to motion, Doppler motions of the Earth and the solar system, etc. But
If the universe is inflating away from me in all directions and there's light coming to me from that same direction, why wouldn't it have a lower perceived speed? Because again, it's inflating away as it's coming towards me.
no, when you say a different speed,
Sorry, a lower perceived speed because, like, let's say I'm driving on the highway. There's a car in front of me and it's playing music and it's driving faster than I am. Or sorry, it's driving a little bit faster than I am. It's riding the universe's inflation and the music's coming back to me. Wouldn't the music reach me at a lower perceived speed because it's now a component of it? It's moving away.
well, there is what's called a dipole effect in these cosmic microwave background measurements. But what I'm speaking about takes account of that and asks the question, what is going on with the universe independent of our motion? And the effects of our motion can be dealt with in these measurements. And when they're dealt with, that's when you find that the temperature that's measured in every direction is pretty much the same. And the only way to account for it, as I say, is if all of these regions were in contact with each other at a very early time in the universe. Another thing that points toward very rapid expansion early in the universe is the flatness of the universe. We don't measure any significant curvature in the universe, which speaks to the size of the universe. And to get a universe of the size for which little to no curvature has been measured also requires this exponential expansion very early in the universe. So these are things that we're trying to test. These are all theory at the moment. There is no proof that this inflationary period happened, except that it makes the Big Bang picture plausible. So one of the goals of the SPHEREx mission is to help constrain what happened during this inflationary period to either reinforce the theory that it happened or perhaps complicate it in a way that maybe makes it less likely that it's the true explanation that accounts for the temperature the temperature commonality that we see in the cosmic microwave background.
What's the degree of inflation right now versus during the inflationary period?
As I say, the universe during this first 10 to the minus 32 seconds was expanding faster than the speed of light. The universe after this brief period of inflation has, I was about to say, been slowing down. It's sublight in its expansion. It's expanding, according to measurements, at about 70 kilometers per second per parsec of distance, which is quite a bit below the speed of light. So the difference between the inflationary period and post-inflation is dramatic.
Okay. All right. So, let's go back to the other work you're doing. So what is hoped to be gained by this, I guess you said 6 months inspection of the sky? Is it over the same, area of space, or is it going to be raster over a huge area, or what?
Well, it will raster over the entire sky every 6 months, and the baseline mission is 2 years. So we will pick the sky with our telescope. We will observe every position in the sky at least 4 times during our baseline 2-year mission. And I should mention for completeness, because I'm actually leading this aspect of the SPHEREx mission, this third goal of determining how much of the key ingredients of life, such as water, carbon dioxide, carbon monoxide, are present in these clouds between the stars, out of which new stars and planets form, and out of which our solar system formed some 4.5 billion years ago. And in particular, we're looking at just how much of these key ingredients for life are resident as ice mantle on small interstellar dust grains. And it turns out that the wavelength range that SPHEREx covers is quite favorable for looking for the fingerprint of those molecules in ice on interstellar dust grains. These have very distinct absorption features that we can detect with SPHEREx. And what we're looking to do is to assess the abundance and distribution of things like water ice in the interstellar medium, because it's the stuff in the interstellar medium that collapses to form the star. And in the case of trying to understand how Earth became habitable, how planets like Earth acquired their ocean. Several years ago, I led a NASA mission that looked for gas phase water in the interstellar medium. And we found gas phase water almost every place that we looked in the Milky Way, but not in the abundance that we initially expected. And we puzzled over that for a long time until we realized that the most likely reason that the abundance was less is that in the interior of these clouds between the stars, there is likely a very large reservoir of water ice. And that would explain a lot in terms of how our solar system is populated by a large number of icy bodies in the region beyond Neptune. It explains why there's a lot of water vapor that comes off of comets and forms the tail of comets when they orbit the sun. And maybe most importantly, how the Earth acquired its ocean. So what we will be doing with SPHEREx is observing almost 10 million lines of sight in the Milky Way, our home galaxy, with the goal of assessing just how much water is present in the form of water ice and CO ice and CO2 ice. And again, when I speak of these ices, I'm talking about very thin layers of ice on top of interstellar dust grains. And to give one a sense of size, these interstellar dust grains are roughly the size of the particles in cigarette smoke. And if you put them under a microscope in the interstellar medium, we believe that you would see that every one of these very small dust particles, most likely in most places, have layers of ice on them.
What do you think is happening with this interstellar material? Like, does it get sucked into the formation of stars? And like, does it get sucked into the beginning, the end? Or, how does it become water on some of these bodies? Like, what happens to it?
Right. Very good question. Stars form and the planets around them form as the result of gravity. So these clouds have internal motion, but every once in a while, you'll have a region of higher density than the surrounding region. And in those regions, the gravitational attraction is higher. And in many cases, it begins to collapse. The gravity pulls all this material toward a central point. And in the center, you'll form the star, but the material that is not pulled into the star has a certain angular momentum to it and will begin to orbit that newly forming star. And it's in that material that the planets form around that star. Now, gravity does not discriminate between gas and dust. So it will pull in the dust, in this case covered with ices, along with the gas in these molecular clouds. And
what if you agglomerate-like material because of the density and it spits out like a comet at some point? Is that a possibility?
Well, it is a very dynamic process, but on the whole, gravity will retain most of the mass in the center newly forming star and in a disk around the star out of which planets coalesce. And Hubble has taken a number of very, very beautiful images of what are called protoplanetary disks. These are embedded newly forming stars called protostars around which you see a thick disk of dust and gas. And if that dust has ice on it, then it is a natural reservoir for imbuing these newly forming planets with materials, volatiles such as water, CO, and CO2.
So you don't think it's possible that material could be coalesced and then I don't know if the rotational speed of a forming star, if it has any, what if it gets to a point where it does, the material does escape on a go-around of this material that's spinning and again go out into space, maybe in the form of a comet or something? Could material be ejected at some point in the formation process?
Well, we do see jet of material from the pole of the newly forming star. So the answer is most definitely yes. It is not uniformly an infall event that forms stars and planets. There is outflow of material, but the net effect when that dies down is that enough material is retained in the disk around the newly forming star to form multiple planets. And we now know of thousands of systems in the Milky Way around which there are orbiting planets. Missions like the Kepler mission and more recently the NASA TESS mission have shown definitively that planets around other stars are very common. So this process that I'm describing of gravitational collapse, star formation, and planet formation can't be a very coincidental or low probability set of events. Nature is telling us that the physics that lead to the formation of planet is straightforward, dare I say, and common.
Could this be considered a cascade, like to form a solar system? Yeah, from what I understand, the sun is 99% of the mass of our solar system. So what would have happened? Would the sun have formed with a disk around it, and then that disk would have, let's say, coalesced into Mercury, and that would have created a disk around it that then would have made Venus and then Earth and on and so forth? Like, would a solar system starting from the star form outward slowly, the planets, or how would they form?
It's fairly clear that planets form more or less in unison. That is to say that gravity will be the driver throughout the disk, and multiple planets will form out of this disk material at different radii from the star. Now, they do affect each other. You can have planets that grow faster than other planets, like Jupiter grew faster than Mars, and these planets can affect the orbit of other planets in the system. So you get a rather wide diversity of solar system architecture around other stars. And by that, I mean there are some stars where we know that their Jupiter is within the orbit of Mercury, if it were analogous to our solar system. And so this process of multiple planet formation is not well understood, but one thing we do know is that it is a very diverse process, and at least initially it can be somewhat chaotic.
Okay, right. Well, very good. I have many, many more questions I'd love to ask you, but we're kind of out of time. Where can people keep track of, the work that you're doing on these three projects and, of other projects that are in process by, people that work with you?
I would refer people to our project website. If you go to Google and you Google SPHEREx, SPHEREx, and Caltech, you will see our project website, which right now does not contain any results because we just launched, and for the next 30 days roughly, we will be checking out the observatory on orbit and preparing it for the onset of data taking, which will be around, April 20th or so. But at the moment, you'll see a description of the mission goals. You'll see a gallery of images of the observatory as it was being built up. And hopefully there are now some images of the launch and deployment of SPHEREx on orbit. But in the future, I'm sure that we will be posting results once the data are in.
Okay. Well, very good. Gary, thanks so much for coming on the podcast and explaining this very complicated stuff. And, I think you're pretty good at explaining it. So thank you so much for being here.
My pleasure.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.
The Kepler mission and more recently the NASA TESS mission have shown definitively that planets around other stars are very common. So this process that I'm describing of gravitational collapse, star formation, and planet formation can't be a very coincidental or low probability set of events. Nature is telling us that the physics that lead to the formation of planet is straightforward, dare I say, and common.
Could this be considered a cascade, like to form a solar system? Yeah, from what I understand, the sun is 99% of the mass of our solar system. So what would have happened? Would the sun have formed with a disk around it, and then that disk would have, let's say, coalesced into Mercury, and that would have created a disk around it that then would have made Venus and then Earth and on and so forth? Like, would a solar system starting from the star form outward slowly, the planets, or how would they form?
It's fairly clear that planets form more or less in unison. That is to say that gravity will be the driver throughout the disk, and multiple planets will form out of this disk material at different radii from the star. Now, they do affect each other. You can have planets that grow faster than other planets, like Jupiter grew faster than Mars, and these planets can affect the orbit of other planets in the system. So you get a rather wide diversity of solar system architecture around other stars. And by that, I mean there are some stars where we know that their Jupiter is within the orbit of Mercury, if it were analogous to our solar system. And so this process of multiple planet formation is not well understood, but one thing we do know is that it is a very diverse process, and at least initially it can be somewhat chaotic.
Okay, right. Well, very good. I have many, many more questions I'd love to ask you, but we're kind of out of time. Where can people keep track of, the work that you're doing on these 3 projects and, of other projects that are in process by, people that work with you?
I would refer people to our project website. If you go to Google and you Google SPHEREx, SPHEREx, and Caltech, you will see our project website, which right now does not contain any results because we just launched, and for the next 30 days roughly, we will be checking out the observatory on orbit and preparing it for the onset of data taking, which will be around, April 20th or so. But at the moment, you'll see a description of the mission goals. You'll see a gallery of images of the observatory as it was being built up. And hopefully there are now some images of the launch and deployment of SPHEREx on orbit. But in the future, I'm sure that we will be posting results once the data are in.
Okay, well, very good. Gary, thanks so much for coming on the podcast and explaining this very complicated stuff. And, I think you're pretty good at explaining it. So thank you so much for being here.
My pleasure.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed. You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.